Most people have gotten a chemical contaminant in their eye at one point or another. Most of the time we can get it out by holding our eyes under running water. In a microgravity environment, astronauts don't have the same privilege. They are expected to find the system, connect all the bulky tubes and hoses, and then wrestle to put the system on. That's why NASA would like us to design a new system. The main goal is to clear the chemical from the eye, but to do so, it has to get water from the source, direct the water to the eye, wash the eye, and then remove the contaminated water. That's where we step in. We are Team 15 working with NASA on the microgravity eyewash redesign.
Our team has developed a single eye cup eyewash design that attaches directly to the astronaut's face. This is supplied by a free-floating water sphere that pins to the end of the capillary straw. Due to the pressure difference, water travels along the tubing, into the eye cup, and up to the surface of the eye. This water covers the surface of the eye, clearing any chemicals. This contaminated water is then guided along the eye cup into the disposal bag. To achieve our required flow rate, a hydrophilic coating would be applied to the system to improve wettability and contact angle. This would be applied to the tubing as well as the 3D printed resin of the eye cup. The goal of our eye cup design is to deliver tepid water as close to the surface of the eye without making any direct contact. If the water is delivered close enough, the naturally wetting characteristic of the eye will cause it to travel across it, clearing any contaminants. This has been demonstrated in space by astronauts on the ISS. The wicking material within the bag will draw out the contaminated liquid and hold it in place until it can be disposed of. Most of our next steps revolve around performing testing in a low-gravity environment to evaluate our system. One example includes the pinning of the water supply to the end of the capillary straw. Our physical microfluidic testing with a PDMS polymer provided a crude example of some of the principles we were evaluating with our system. But the gravity was still a very large influence, and a testing environment in the ISS or on a parabolic flight or drop tower would better evaluate the performance of our system. This type of testing would also help us to evaluate our requirement of water loss, which is a very important concern for NASA.